chemical properties of group 1, or let's say of alkali metals. So it's either you call them group 1 elements, you call them the lithium family, or you call them alkali metals. Now, number one is that, why are they called alkali metals? We said that earlier, that they are called alkali metals because they react with cold water to produce an alkali and then liberate hydrogen. So, if you pick any of the members of group 1, which is, let's pick sodium for example. Sodium in its solid state reacts vigorously with water. And what would this give us? It gives us an alkali, right? And liberates hydrogen gas. It gives us an alkali and liberates hydrogen gas. Now, the next question we need to ask ourselves is the equation balanced? No, the equation is not. So, to balance the equation, what if we do this? Make sodium here 2. We make hydrogen 4. We make hydrogen 4 and oxygen 2. Now the equation is balanced, right? So they react with cold water to produce an alkali and liberate hydrogen gas. Let's find a space to put that. Sorry, let's erase this. So they react with cold water. They react with cold water to produce an alkali and liberates hydrogen gas. So that's the first property. Let's take another example. Which other member of group 1? Let's use potassium. So we have potassium also reacting with very cold water. You put it, you can signify that it's cold, to give us potassium hydroxide in its aqueous form and liberates hydrogen gas. This reaction is very important because number one, care has to be taken so that you do not mess things up, all right, in your laboratory, because group 1 elements are highly reactive. We'll talk about that under the chemical properties. They are very reactive. The reaction with water is explosive. So what that means is when they react with cold water, it could cause an explosion. All right, you could have an explosion of, you could spill the alkali, which is the NaOH or KOH on your face. So what you do is, number one, you ensure that the water is very cold, so that even when the temperature of the reaction is raised, because it's highly exothermic, when the temperature is raised, it will be raised somewhere within limits, right? Number one. And number two, make sure you use an all-glass apparatus, so it doesn't melt the rubber or plastic or whatever apparatus you are using. You use an all-glass apparatus. That's another point. And then this reaction also tells us that if you are asked to describe a laboratory preparation for hydrogen in the laboratory, for example, and what you do is you can give this equation as one way to prepare hydrogen in a laboratory. Action of sodium on cold water. What will happen? It will give you sodium hydroxide and give off hydrogen gas. That is how we can produce hydrogen gas in the laboratory. It is one of the numerous ways, right? We can produce hydrogen in the laboratory. Or you say action of potassium on cold water. You get an alkali and you give hydrogen gas. Hydrogen gas also is produced, and that's another way to produce hydrogen in the laboratory. This is also another way to produce alkali. To produce alkali, you react group 1 metals on cold water and it gives you an alkali. So you can see that chemistry is sort of intertwined. Understanding one concept helps you understand another concept, right? All you just need to do is you need to figure out a way of interpolating ideas, right? So that once you learn something in a course, you can apply it to another course. And that's it. Now, it's important to state here that group 1 elements have a very high affinity for water. So it means that in the presence of water, group 1 elements will be converted to an alkali and they give off bubbles of hydrogen. Now, for this reason, we don't expose group 1 elements to air because you know one of the composition of air is moisture. You have moisture in air. So to prevent the group 1 elements from reacting with water in air, or preventing them from reacting with water, all right, carelessly reacting with water, we store group 1 elements under a layer of oil. So the best way to store sodium is keeping it under oil. The best way to store cesium is keeping it under oil. And the reason is not far-fetched. The reason is because being a group 1 element, they have high affinity for water and they are best kept under oil, right? So that is one property. What other properties do group 1 elements have? Being group 1 element, okay, before that, they have one valence electron. They have one valence electron. All right, so let's see. Or you said they have one outermost electrons, right? One outermost electron. Now, sodium, okay, let's start from lithium. Lithium has an atomic number of 3. Sodium has an atomic number of 11. Potassium has an atomic number of 19. We would analyze lithium and sodium for you and leave you to analyze potassium yourself. What is the electronic configuration of lithium? That is 1s2, 2s1, right? Or you say 2, 1. Then what about sodium? Sodium has an atomic electronic configuration of 1s2, 2s2, 2p6, 3s1. Or you say 2, 8, 1, right? And then you can do for aluminium. Or for potassium, sorry. Then what do you notice here? You notice that the outermost electron of lithium is located on the 2s orbital, and it's just one of it. The outermost electron of sodium is located on the 3s orbital, right? And it's just one. But you analyze for potassium, the outermost electron will be on 4s1, right? And it means that potassium there has one valence electron, or you say one outermost electron, and that's why they are put in group 1, because the number of outermost electrons you have tells you the group you belong, right? Okay, what other property do they have? They ionize by loss of one valence electron. Ionize by loss of one valence electron to form a unit positively charged ion. What does this mean? Let's take the structure of lithium and sodium again and explain with this. We said sodium has 1s2, 2s2, 2p6, 3s1 configuration, and lithium has 1s2, 2s1 configuration. So if we draw the structure of lithium, right? This is lithium with 2 electrons here and the third electron outside, which means it has one outermost electron. And we do the same for sodium with 2 electrons here with 8 electrons here and outermost 1 electron. The structure of sodium should be bigger than that of lithium. So permit my diagram, and I think it's even bigger. Okay, now what do you notice? That lithium can give off this 1 electron to form a stable duplet, right? So if lithium gives off an ion, it forms a stable duplet. Why? Because the first shell needs just 2 electrons to be stable. And if lithium loses this electron on its outermost shell, it would have the shell inside left. It means if lithium loses that outermost electron, it has this left. That's the lithium ion. So this form of lithium is a more stable form compared to the initial structure, or the initial diagram. So what does that mean? It means that ordinarily, group 1 elements would want to lose their outermost electrons, right? And then losing the outermost electrons allows them to attain stability.